So, I'm Massimiliano. I am a software developer working at Sylabs, and what I will talk about today is basically a brief introduction to Spack, just to keep everybody on the same page here, and then updates on what has been going on in Spack's world during the last year. So, but before we start, I just want to spend a few words on Sylabs, Singularity, and Spack, and the relationship of the three things. So, as many of you, I'm pretty sure, are already aware of, Sylabs is the company that backs up Singularity's development. And well, Singularity is known by everybody. It's a container runtime that was designed with HPC in mind. You can basically see it from each and every feature it has, from the image format, which is single file, it can be signed, from the integration it has with containers, from the native support for accelerators like NVIDIA CUDA or AMD ROCm. What I want to say is that with the status that is there right now, Singularity already brought mobility of compute to the HPC world. It's kind of easy to move images between machines, and yeah, that's already there. What still is difficult, or not as easy as one would like to, is to build the images themselves. And that's why Sylabs started to sustain Spack as a project via my developer time, in order to better integrate it not only with Singularity, but in general with the HPC runtimes that are used. So that's just to give a brief introduction on that. And that said, let's get started with a brief 101 on Spack. So Spack is a package manager. The lead developer is Todd Gamblin from Livermore Laboratories, is also the original author from, I think, 2013. It's the first time that Spack was publicly released. Spack tracks metadata for all the software it installs, and it can permit multiple configurations of the same software to coexist at the same time. It has support for supercomputers, Linux, and macOS. It can install from sources, and that's, I would say, the primary mode still, or from binary packages, because you can package binaries once you install something, sign them, and then distribute the binaries or reinstall from them. It has a very active and engaging community, and to what regards licensing, it's dual licensed. So it's either Apache 2 or MIT, and whenever you use Spack in your project, you just pick the one you like. And here you have also a link to the home page of Spack. Who can profit from Spack? I would say mainly four kinds of users. The first kind is end users of HPC software, so people that just need some HPC application, and they can use Spack to install it seamlessly. The second kind is HPC application teams. Usually people that are focused on maintaining a particular HPC application or a set of applications, and they want to stress all the build configurations, and they can leverage Spack to do that. And we'll see later how you can do it very easily with the Spack syntax. Package developers, people that just package software, and finally, user support teams or sysadmins at HPC centers, basically to install all the software stack that is provided to users. This is a very old picture, so apologies. Well, and you don't see the word in here, but yeah, it's like America is supposed to be here, USA, Europe, and this is just to say that Spack is used worldwide. This was a picture of sessions on Spack Read the Docs, so our documentation for 1 month. But yeah, the bottom line is that it's not a local project. It's been used worldwide. It's the way the exascale computing project will deploy all their software. So Spack has been designed since the very beginning with simplicity in mind. If you want to start using it, all you have to do is either clone the repository if you want to use the bleeding edge, or just untar some point release, source an environment script, and then you're ready to go. You can start using Spack, and for instance, Spack install HDF5 will install HDF5 along with all its dependencies. And not only we try to make it easy for users, we also try to make it easier for packages. Packages are Python classes. I would stress one difference here. A package in Python represents all or describes all the build configurations for that package. So in this case, the class Kripke describes all the possible build configurations for Kripke. And in that sense, you could say that a recipe in Spack is a sort of a template, as opposed to EasyBuild, where things are pinned down. So each EasyConfig is a particular version, right? And so on and so forth. I was saying we try to make it easy for packagers. We provide tools to work with packages, to create them, to edit existing ones, or to check some new versions. And that's basically a whirlwind tour of what Spack is. So before going to the updates, I would like to talk a bit more in depth of 3 core concepts that are crucial to how Spack works. So the first one is spec syntax plus directives plus concretizer. And those 3 things together constitute the engine of Spack. They are what makes Spack works. The spec syntax is the way a user can interact with the tool and describe what Aris needs. Whenever you install something, you can be generic. You can say Spack install HDF5. If you just mention the package, basically you're telling the tool that any version of HDF5 would do. But you can be much more specific than that by employing this syntax. So you can specify a particular version with the @sigil and say HDF5 at version 1.10.1. You can specify which compiler you want to use if that matters to you. You can turn options on and off. Those ones, like the plus stip, is called variant in Spack parlancy, and it's basically an option that will affect your software configuration. In this case, very likely, it activates support for stip. You can inject flags directly into the compilation, or you can target different backends. So spec syntax is how the user interacts with the tool. On the packager side, you have directives in the Python classes that describes how to build a package. Directives model the allowed configurations, and they are declarative in natures, like this version directive or this variant directive. And this way of modeling things makes it such that you have to deal with a combinatorial space in HPC, because you need many compilers, because you need many configurations or many versions of the same things. With directives, you model each elementary piece and you build up the space from there. So for instance, here we have 2 versions and 2 Boolean variants. This is already a space of 8 items that you can search, not accounting, of course, for the different compilers, for the dependencies that could be listed, and so on and so forth. And you have also directives to basically nullify parts of a search space. And yeah, you have other directives to specify dependencies. So basically, directives model the allowed configuration in a package. And finally, there is the last bit. So you have users that with the spec syntax tells the tool what they want to build. You have packages that describe what is the search space you can employ. And there is the concretizer that brings the two things together and basically fill in the blanks of what the user didn't say. Maybe you are just interested in the version of HDF5, but you need nonetheless to do a proper installation, a lot of other details. All those details will be chosen by the concretizer based on what's in the packages. So in other contexts, what we call the concretizer would have been called a constraint resolution algorithm. You basically read your constraints from the packages and you enforce them with some logic if the user didn't specify otherwise. Usually you could hear that, let's say in SPAC world or in the SPAC community, that the abstract spec, the user requirements, is turned into a concrete one, which is what is actually installed with all the details. And that concrete one is basically modeled by a directed acyclic graph with a lot of metadata on both nodes and edges. And that metadata can be, of course, hashed. The entire graph can be hashed. And whenever we install software, we use the hash to identify the prefix of where that particular software will be installed. And that's how we can manage to have different configurations of the same software to coexist with each other. So all the software is installed in the same place in the SPAC store. And that's all based on this mechanism. So if I have to sum it up with a slogan, I would say that SPAC fights combinatorics with combinatorics. We have to model a combinatorial explosion of things, and we have directives and ways to model its elementary pieces and fight back, with the same currency somehow. The second core concept is that we have a database of installed packages. So whenever you install something with SPAC, you build up a JSON database of things with a lot of metadata on what has been installed. Metadata that can be if the request was explicit, like, is this an implicit dependency that is needed to satisfy some user request, or it's actually something that the user requested explicitly. A reference count, an installation time, and a lot of other things. And this DB is usually located at the root of the store, so the place where we install all the software, in a .spackdb folder, and the name is index.json. Not only we do that, but whenever we install things in an hidden directory of the installation prefix .spec, we also put metadata that is related to the software that has been installed there. For instance, files that is worth archiving. This is an AutoTools package, so we archive the config.log. We have a dump of the build environment, a dump of the build logs, all the recipes that were involved in this software, so all the recipes that were involved in that particular deck, and the dump of a graph in YAML format. So having this information might be redundant, but gives, I would say, a lot of robustness, because in case, and I have to say this doesn't happen frequently, so I'm not saying that the JSON-DB gets corrupted, but in case it gets corrupted, you can reconstruct it from all the metadata that we have distributed into the store. Then, once we have all those information in a database, we can start, and we indeed started and built a lot of commands on top of that. So query mechanism, for instance, with SPAC, you can easily ask what is installed, and you can make more powerful query than just simply, hey, do I have Zlib installed? You can ask, hey, what did I install since a month ago? What did I install with GCC 5? Or what do I have installed that depends on this particular version of OpenMPI? And likewise, you can also uninstall things the same way, specifying, I don't know, uninstall everything that was compiled with Intel, or uninstall everything that was used in OpenMPI, and so on. Finally, you can also generate module files on top of that. This topic is kind of long. I would refer you to the tutorial that is linked here, but in a nutshell, we support flat TCL naming scheme, so TCL module files, or hierarchical module files generated in Lua, so in Lua format. They are both highly configurable in many aspects. So second core point, we have a database, we can query what's installed, we can uninstall software and do a lot of manipulation of the things that are there. Finally, third concept before going to the actual updates, every time we compile something, compilation is mediated by a thin wrapper script. And yeah, I hope you see the blue here. But basically what happens is that when you install something, we have, let's say, master process with a clean environment. We fork a new process because maybe the build environment needs something to be set up and we want it to be clean for each software we install. We set up the new environment and then we start to go through a set of phases that depends on the underlying build system. For instance, if it is an AutoTools package, it would be configure, make install. And whenever we compile something, each compilation line is mediated by this thin wrapper that can, for instance, shuffles flag around. It can inject include flags or library search flags. It injects actually RPath flags. Everything you build with spack is by default RPathed, so that application works the way they were built. They can always find their dependency. And you can optionally configure spack to use runpath instead of RPath. Another thing you'll see later, we use this wrapper to inject microarchitecture specific optimization flags into the compilation. Okay, so I would say this is a good point if anybody has some quick questions. Otherwise, I'll go on with the real updates from last year in chronological order. Well, I get everything is clear, but it's just very late in the afternoon. So, first update, first features added since last time we talked about spack. Now we can chain together multiple instances of spack. What does that mean? We've talked about the database. So you can imagine something like that. This is a feature mainly for facilities. You might have a central instance of spack used site-wide, in which you will install software that is used by the entire community, by all of your users. So software that is common to everybody. Then you might have different departments that you support at your site or university. And those departments might be interested in software that is their own software and is not meant to be used by other people or is of no interest to other people. One possibility we offer is that those guys can use another instance of spack, can configure that instance to point to the upstream database and use all the site-wide packages as read-only. So whenever they install something and a package is available upstream, they will reuse it. And if they need something that is I would say, more peculiar to their own needs, then they will install it. It won't pollute the environment for anybody else, and they can do whatever they want with that. And they will have their own local database, which is writable, and the upstream will be just read-only. And if you want to take it to the limit, you can go and have a chain of those things down to the single user that basically hooks up on the departments, hooks up on the central repository, and it's back all the way down. So this is one of the features we added. You can basically chain different instances and use whatever other people already installed as read-only. Okay. Second one is improvements on Spack environments with I would say, a quick introduction on what are environments. Spack environments are meant to give users portable and reproducible builds. And they virtualize a Spack instance. If you ever worked with Python virtual environments, you can think of Spack environments as Python virtual envs, but for anything. So for C++ applications, for Fortran applications, that's it. And here you can see that we provide quite convenient command line interface to interact with environments. Nonetheless, like at the core of the environments, there is always a manifest file called spack.yaml that at least contains what we call the root specs. Those are the specs that the user wants to have in the environment, and they are abstract by definition. And in the spack.yaml file, in this manifest file, you can finely tune the configuration for the environment. You can finely tune each and every part of the configuration. So the mirrors it's going to be used, how modules are going to be generated, which repositories you want to use, preferences for the concretizer, whatever. And that's because each environment is meant to satisfy some particular need, and so it should be possible to customize it that way. The spack.yaml doesn't have to live within Spack. It can be bundled with whatever. So if you need to ship an environment with your software and you want to use Spack, just like ship this spack.yaml to recreate the environment. It can be manipulated directly if it is in the present working directory, and we provide commands to do that. Whenever you concretize it, whenever you ask Spack, okay, I have those abstract requests, but what will I install actually on this machine right now? A log file will be produced on the side called spack.log, and this thing will contain each and every detail of the actual installation that is going to be performed. And using either the spack.yaml or the spack.log file, you can recreate an environment. If you just use the manifest file, you can recreate it logically. It will be the same abstract user request, maybe on another machine, that will concretize slightly different. Because, I don't know, it's a different architecture or whatever. If you want to reproduce exactly what you have built just right now, you will use the log file, of course, on a similar machines, because the log file will contain, I would say, assumptions on where it's going to be built. So one thing that we added on top of environment to make them more usable is views. Views are directories that you can have, that you can configure to have wherever you want on the file system, with all the packages listed in the environment that are sym-linked in, with a structure that resembles the usual Linux structure. So all the executables in /bin, all the libraries in /lib, all the common stuff in /share, and so on. And basically, we can manage the complexity. We can, manage this combinatorial build. But in the end, we can also make simple things simple again. If you want to have a view on a few applications on a large store, or you need to have a lot of those different views, you can configure them, and you will have those, let's say, folders in which things will be symlinked in and can be used like in any normal Linux box, except it will be software that it's configured exactly like you wanted. The other thing that we did, and that's aimed in particular at HPC sites, is to include a metrics syntax to specify the specs in a spack.yaml. So you can give definitions that you can employ later. For instance, here I define what does it mean compilers. And here I build a matrix out of 2 lines, basically saying to do a Cartesian product of its software here with its compiler there. And you can have more than one matrix, and there are like ways to exclude part of their Cartesian product. Where is this useful? I think it's kind of apparent, but this is useful to describe the entire software stack for an HPC site. You can have this single file built with this metric syntax, and when you say spack install, it will install your entire stack. And that was also an addition like done last year, always part of Spack environments. Okay, this one is an interesting one. Spack can optimize for specific microarchitectures. So up to version 0.12, the support for microarchitecture was coarse-grained. Basically, if you asked back then the architecture that was detected by Spack on a given host, you will get an answer like x86-64 or AArch64 or PPC64, because what we were doing back then for architecture was to rely on Python's platform.machine, which is basically uname-m. And as a result, we couldn't build software with microarchitecture specific optimization automatically. So no flags are injected into the compilations. Since Spack is 0.13, we have a much finer notion of architectures. If you ask right now which architecture is detected, you won't get a generic x86-64. You will get something more like Broadwell or Ashwell or Skylake AVX 512. And you can query at any Spack version what are the known targets. I think that right now we support 43 microarchitectures that have been modeled. And host detection, so we have a static knowledge of those 43 microarchitectures. Host detection is done on a best match of what we know about the architecture and what we detect on your host. This is just to say that if you use a Spack in the future old enough and you are on a new enough architecture, like it happens with compiler, you'll get probably the best match, meaning some ancestor of your current architecture, because Spack doesn't know yet any better. So, but that's basically what compiler do. What did it enable in terms of building software? Well, now when we build for a specific microarchitecture and we detect it, we are able to automatically inject optimization flags. So whenever you ask build for target ice lake and you have a given compiler, Spack knows what are the flags to be used to optimize for that target using that compiler. Also, the concretizer is aware of compiler support. So if you are using an ancient compiler and you are doing it without specifying explicitly the target that you want to build for, you'll just receive a warning like that, and your target will be somehow demoted. In this case, this is done on my laptop. It's a Broadwell. If I try to build with GCC 4.8, but is old enough to not know how to optimize for Broadwell, Spack will tell, hey, warning, you're using an ancient compiler. I detected Broadwell, but actually I'm targeting Ashwell because that's what this compiler can do. If instead you add an explicit request on a target that is not supported, Spack will error out with a sensible error message saying, hey, you asked me to build software optimized for, I don't know, Skylake with GCC 4.8, but I can't because support for Skylake starts at this version of GCC. And this is what happens on the user side. So the user facing modifications that is enabled. On the packager side, the fact that we have a notion of microarchitectures permitted us to remove a lot of variants which were tweaking architectural aspects of a recipe and that were like thrown on the user. That's what we could do before, and that are now automatically detected. So there is logic right now in packages like FFTW or OpenBLAS that based on the target that you asked Spack to build for will query that target and ask things like, hey, is AVX 512 available in the target that I'm using? Yes, okay, then use this configure option. Or is BMI 1, is neon there? And this simplified a lot a few well-known packages that are, using especially SIMD instructions to build. We also have a notion of, I would say, subset type comparison of architectures based on the features that each architecture has. So if you say something like that, what you mean is this target strictly more capable than Broadwell? Meaning, is anything built for Broadwell also running on this target? If yes, then append this flag. Otherwise, no. And those are all queries that we can do. And we actually started pulling out all this logic into a separate project. And that's a joint project also with Kenneth. So it's at the moment me, Kenneth, and Todd, but yeah, it's open source and anybody can contribute. So this library is available if you want to integrate it too with EasyBuild. Another addition, this is quite fresh, okay?
Question. 1 second.
So the question is, what is the name of the library? The organization and the project is called ArcSpec. Right now the library is called also ArcSpec, and you'll find it on GitHub. We just have Python packages. The intention is, so everything here is based on static data that describes the microarchitecture, and that's stored in a JSON file. And then we have the bit of logic that does detection or comparison, which is a Python layer on top of that. That Python layer and the JSON data are stored in 2 different repositories as part of the ArcSpec organization. Right now, we just have a Python package, but the intention is to provide bindings also for other languages. So this is, I would say, strictly a bit outside the Spack update, but it's worth mentioning. One of the things that this library can give is some sort of standardization on naming. And I would say, on the grain on which we could talk about microarchitectures. So for instance, before I've seen that we were grabbing proc CPU info, which gives you back information at a much finer level. It gives you back hardware information, like which exact processor are you running on. But in the context of building software, this is too much. Like, what you want to know is the instruction set that you can use on that processor, not if it is like a slight generation different from the other one. And basically with this project, we are also trying to standardize the naming for that. So we generally started as a good guess by using whatever GCC was already using, or GNU was already using. As I said, we have 43 architectures which are kind of relevant to HPC, and the software is open source, so hopefully we'll get more contributions. Yes, Victor.
So do you have a mapping also between do you also have a mapping between because you use mtune and march and you say Broadwell, but for instance like PGI uses a different naming scheme, so you also have this mapping to different compilers?
Yeah, so each architecture in the JSON file has basically a compiler section which does that mapping. And frequently you have more entries for the same compiler family because, for instance, a few flags change over time even for the same compiler family. I think I need to look that up, but there are things that were called like core i7 at some point and then switched to a more human understandable name on later versions, and that's all mapped there. So if you use ancient compiler, you will pick the correct flag. If you use Intel or LLVM compilers, you will pick the right flag, as long as somebody put that information in the JSON file. Okay, I was saying a pretty new feature that has been added by a couple of days, since a couple of days, is that Spack integrates with GitLab CI pipelines, and that's also an extension to Spack environments. So there are sections in the Spack environment configurations that you can write to be able to automatically generate with Spack .gitlab CI YAML. And that's the grand idea that we are pursuing, and we are pretty close to it, to have a CI infrastructures for source and binary packages. So the basic idea, that started like a couple of years ago, and we are pretty much there. The basic idea is that a user can not only build things from sources, pulling from, let's say, where its source is hosted, but we could also mirror the sources somewhere in some central place. I mean, even just for reproducibility or robustness. And on top of that, we can also produce binary packages. And we can do that in CI frameworks. So if you have an environment like the one I've shown before, you can use it to run on GitLab CI, try the build, package the binaries, eventually sign them, push them wherever you want, and then upload the result to some dashboard that is like online. So right now, the dashboard and where you push the binaries, should be somehow self-hosted. There is no Spack organization official place where to put those, but it will come. Anyhow, all the pieces of this infrastructure are already in place. One point to notice is that the GitLab CI runner has been also modified to run, on cray systems where security is really an issue by employing SUID. So basically, you will run this thing that as soon as it goes into the batch system will become you. And people will know that, well, it will have your privileges and it will be you running. So you can go at HPC centers, which have very high concerns on security, and still produce binaries for gray machines or, top 10 machines of the top 500, which are kind of different from the usual clusters. On the other end, you can produce binaries for the usual x86 clusters that you have or whatever. And later on, when people reinstall, they can point to your binary mirror, which, I don't know, it's probably signed. They can trust that you build the thing and build from there. So they could get the best of both worlds. The one-off source package managers that can build optimized for the machine, and the one-off binary package managers that install in a snap. So another thing that I hoped it would be in, but it will be in by end of the week, is that Spack can generate recipes to build container images. That's also based on Spack environments, which is a sort of, baseline for a lot of advanced features. The basic idea is that you can control the metadata with which you generate images via the container attributes of environment. It's not a mandatory attribute. We'll provide sensible default. All the recipes we will produce are based on multi-stage builds. The initial build stage will be one of the Spack-enabled images that are provided by the Spack organization on Docker Hub. So whenever we push to develop, we have an automated process that builds a Docker image. Currently, we support for base operating system, CentOS 6, CentOS 7, Ubuntu 16.04, and Ubuntu 18.04. And the second stage will be just a stage with your application, and I would say anything that can be taken out will be taken out, and your application will be available in the path. How does this work? Well, basically, it works by having a spack.yaml somewhere, and then you just call this command, spack containerize, and that will print to standard output the recipes. The recipe that you can use to build, in this case, a Docker image with a Docker file. Of course, we have support for Singularity dev files, so that's one of the things that you can tweak. You can say, hey, the format should be Singularity. It's also multi-stage. A quick note, if you want to use this multi-stage build with Singularity dev file, you need the upcoming 3.5.3 versions. I mean, it's coming in a couple of days, or you need to work with master currently. But yeah, just wait a couple of days. And yeah, so Spack can generate recipes to build those images. And it's based on environment, so it's as easy as it can get. You can just say, I want to install Romax with MPICH and whatever. Spack containerize, here is the recipe, and you build it. Okay, another one that is kind of easy to explain, not so easy to implement. So yeah, I should thank Tamara from Livermore for doing all the implementation. This was really hard. Spack supports concurrent or parallel builds of software. So right now, what Spack could do, and this will be in also by the end of the week. Right now, what Spack can do for parallelization is to parallelize its single build by employing make-j and it make-j or similar things, and it does that since quite some time. What this can give you is to parallelize at the package level. So you can have basically multiple Spack processes that proceed independently, and they coordinate each other via file system logs. So what this enables is, in a couple of words, to send a batch job and say srun spack install some software. You will spawn a few processes. All those processes will have a build queue. They will try to install things, check if the thing is already installed, and they basically synchronize with each other using file system logs. And this is like a simplified version of the algorithm, but that doesn't take into account, I don't know, external builds or other fancy things, but it works. And it works seamlessly across, different schedulers. We don't have to interface with schedulers API. And it gives us both parallelism, because it can be you that spawn different processes that have to work to coordinate to install the same thing, the same DAG, or concurrency, because this also coordinates different users that are using the same Spack instance at the same time to build asynchronously. Finally, coming soon, and by soon, I would say, take May with 90% confidence, I would say May, new concretization algorithm. So right now, to do constraint resolution, we have an ad hoc algorithm which has a few drawbacks. For instance, it doesn't take into account what you have installed. It doesn't take into account what you have available in the binaries. And other than that, a few of the steps are done of constraint resolution are, let's say, done in a certain order and then set forever. For instance, the architecture that you will use is selected in one of the first steps, and then it's done. It's that architecture. What we will provide is a new algorithm. Todd has been working hard on that can lift all those limitations and basically do a proper constraint resolutions where all the constraints are solved together, but will also take into account the binary specs that you have in the mirror and what you have installed. So from the practical point of view, this means that, for instance, you want to install 10 times a CMake because you have to be consistent with compilers or things like that. And if you ever used Spack, you know what I mean. Like if you have a DAG that is installed with a certain compiler, Spack right now tries to enforce that compiler if you're not specific throughout the DAG, also to build dependencies. With this thing, there will be a notion of build dependencies, there will be rules to treat them differently, so it will be smarter. It will take into account things that have been already built by others that maybe are trusted at your side. It will be just better. But yeah, it will come in May. And I'm done. So thank you very much for listening. And if you have any question, I'm here also tomorrow. If you want to switch over to the other side, just contact me.
Dark.
Thank you.
One question I had when you were talking about the target architecture support that Spack has. So
Yeah.
when you tell it to build for Broadwell, that it uses march Broadwell, mCPU Broadwell.
Yeah.
Why has Spack never used march native?
So the point is, march native is not something that is portable if you package binaries. Because how do you tag something as native? It's native here and right now.
Yeah.
But I can't package that and ship it to your machine.
But that's the same issue if you're building for Broadwell and I have a Sandy Bridge.
Yeah, if you have a Sandy Bridge, I have the information that this is Broadwell, and in the binary package, I retain that information. So that's the point.
That's a matter of tracking what the host has as architecture. It's not a matter of using...
That's a matter of tracking what you're building for. So if you are on your machine and you want to build, I don't know, on my Broadwell laptop, I can still build things It's also a first step towards true cross-compilation.
Right.
But right now, we didn't go as far as making it simple to have true like cross-architecture, cross-compiler. But you can still like build for Ice Lake on my laptop and tag the things you build as valid binary packages for Ice Lake. If you do native, I mean, there have been talks of allowing that and not allowing to package those things. But yeah, that's something that it's out of your control. It's like, okay, do the best you can. And that's it.
But you can still build. So you can still build for native and tag your binary with the architecture of the build system, right?
But how can you be ensured that native does exactly the same thing as Broadwell or as Ashwell? So I wouldn't be personally confident enough on my knowledge in each and every compiler to ensure that. And I think there would be differences.
I think even if you're using mArch native on a Broadwell or you're using mArch Broadwell, it's not the same thing.
Exactly.
Yeah, so there are, I don't know what the difference is, but there is a subtle difference between both.
So when you use those things, that's ensured to work on a Broadwell, always. So, yeah.
So I have a question regarding your Singularity def generator.
Okay.
Why do you create a spack.yaml and not a spack log file? Because with the spack.yaml, as I understood in your presentation, this can lead to different concretizations of the...
So the spack YAML is what you want to install, okay? The spack log you cannot generate yourself. It will be generated as part of the installation process. You can like pin the things that you are interested in so that they will be resolved like you want. For instance, you want to, if you want to build for a given architecture, you can specify it here. You can say, hey, the target should be this one, not my local machine. But you cannot possibly generate the spack log yourself.
No, but so I'm not saying you should generate it yourself, but because this is integrated with Spack, right? So Spack should write the log in the Singularity def. Otherwise,
It
runs
indeed does in the image, and in the final image, you will have the log file, and you can see what was installed.
Yeah, but I cannot give the Singularity def file to another user and be sure that the installation will be exactly the same in those Singularity builds.
So you cannot give the Singularity def file and be sure. I guess that this is in some sense true. In the same way, it is true that you cannot give an EasyBuild file to somebody that is on a PowerPC and you are on an x86 and you say, hey, build on the PowerPC the same thing that I built on the other.
It's worse than that.
Yeah, but it's not just the architecture. So if I use the Singularity def today and I use it in a month in the same machine, I may end up with different results. That is my point. It's not just migrating it between architectures. It's in the same system.
Well, in the same system, you can pin down to a point release, and that won't happen. So once you configure Spack, the concretization algorithm, if you run it again and again and again, it's not like randomized. If you're telling me, okay, I leave a few things hanging in the configurations because I'm not interested in that, I move this file to another machine that has different configurations, then what would Spack do? Is it possible that it selects other things? Well, maybe. But if you pin those things down, it will be like you wanted. And if you redo the same thing on that machine, it will be exactly the same.
Okay, yeah. But yeah, as long as it's the same Spack version, yes.
Yep.
Can you return one slide, please? Back.
Okay, so like which one? This one?
So on the Docker, you said you wrote something like spec develop, something like that.
Yeah, that's like the bleeding edge. So this thing is moving, but we also have like point versions. So if you say spack 0.14 dot something, that will be like the commit hash.
Can you also take the commit hash from develop? Can I do develop and then I don't know with the commit hash?
Not right now. Not right now.
Okay, because that would be nice to actually guarantee that you have reproducibility, right? Because you actually have the exact version of spec.
So you want to be able to pin that. I need to check how far this Docker up goes, because with develop, we basically build a new image at every push. So I really need to check if they store all those images forever.
I see.
The tag is moving. So latest is always the latest.
So if you want to share this the Docker recipe, or then if you have pinned the spec, you're gonna get.
I would say that if you want stability, you should go with a release, at least right now. But if you want to share it, yeah, and reproduce it.
I have a question concerning tool chains. So do you guys aim to do any tool chains or a broader version of tool chains like EasyBuild does, combinations of compilers? Because as soon as you do RPath, what happens is that you can do module load OpenMPI, let's say, start with spec, and then if you do GCC minus version, you're gonna get the GCC from the system, but OpenMPI could have been installed with another GCC installed by spec.
So I don't know if I fully follow that, but that's our way of specifying tool chains.
Yeah,
for
but
installation.
when you do module load, the user, if the user, I say, you do compiler the GC71, like you say, and you have like OpenPI, and then what happens is that if the user does module load OpenPI, he will be getting the MPICC with GCC71, but the GCC of the normal GCC command will be 481 from, I don't know,
So-
2.7.
So your question is basically, how can I make it such that users could use software installed by spec via modules in a consistent way? I would say via Lua hierarchical modules. That's at least the best way that I could do it back when I was working at BFL. You need to configure that, but you can definitely make it such that you don't have the wrong MPI available when you load a compiler, you don't have the wrong BLAS available when you load an application, and so on. It needs a bit of configuration because, of course, the more things are flexible and each site wants its naming, its layout, and whatever, the more you need to configure them manually.
Okay.
Okay, let's wrap up here because I'm getting hungry.
Yeah,
Thank you very much, Massimiliano.
you're welcome.